Thank you so much to Emma and Jeremias for inviting me. I'm Edwin. I'm going to be presenting some work that I did during my PhD at the University of Oxford, jointly with Chris and Stephen. And these days I'm actually in industry, but I should be making a short return to academia soon. And the title's a little bit vague, Martingale Posterior distributions. So I'll go through it slowly and talk about kind of all of the core ideas. So I'm going to start with an introduction. We're going to go through a somewhat novel interpretation of what we think Bayesian uncertainty is. We're going to introduce something called predictive resampling, which is going to have really close ties with the Bootstrap. And then I'm going to go through some of the related work. So this will be the introduction, and then we will formally introduce what the Martingale posterior distribution is after this introduction. So I think it's pretty clear that within the field of statistics and machine learning, there's been a really big focus on the prediction of future outcomes. We're building bigger and better models to predict things like languages, images, and just data in general. But there's still a really big interest in many settings, such as the pharmaceutical industry, for example, where we're interested in statistical inference instead of prediction. So one framework for this, which I'm sure you're all familiar with, is the Bayesian framework. Usually the Bayesian framework, you start with a prior on some parameter of interest, and then you go through the usual prior likelihood machinery. But today we're going to look at a new perspective. We're actually going to start with this predictive distribution. I'm going to write here P of yn plus 1 given y1 to n. So y1 to n will be our observed data. Yn plus 1 will be a future data we haven't seen yet. And we're going to use this as a starting point for Bayesian inference on a parameter of interest. So I have this little kind of diagram here, having this bidirectional arrow from prediction to inference. The arrow from the right-hand side to the left-hand side is usually quite well understood. We're going to talk much more about the left-hand side to the right-hand side today. So just a crash course for, and also to introduce some notation for conditionally IID distributions in the traditional Bayesian framework. We're going to illustrate the sampling density as f subscript theta. Theta is going to be some parameter. For now, we're going to assume this is finite dimensional. Then the usual kind of traditional Bayesian approach is to elicit a prior, pi, which is going to be a density on theta. And this is supposed to represent your knowledge as well as your uncertainty about this parameter of interest. You're going to see some observations, y1 to n, which you've assumed is conditionally IID from f theta. And Bayes' theorem is going to give us this classic posterior density, which we can then use for decision making. So it's simply the ratio of the likelihood times the prior divided by the marginal likelihood. Now, one tool that comes up a lot in model selection, for example, but also in prediction in general, is to compute something called the posterior predictive density. So this is going to be the integral of the likelihood over the posterior for a new data point. It's going to represent your subjective predictive distribution on the data point yn plus 1, given what you've seen from y1 to n. And today we're actually going to start with the thing on the left, and we're going to kind of work backwards and kind of figure out how this is connected to the Bayesian posterior. And I'll talk a little bit more about why that's going to be interesting.
Can we just see what the comments are in the chat? I don't know.
Yeah.
Just in case people can't.
I can hear. Okay. Sorry, I cannot hear anything. Yeah.
I think just carry on.
Okay. So at the core of the idea of the paper is to ask this question, which is a little bit vague. But we're going to be asking, what is the source of statistical uncertainty? And I think both Frequentist and Bayesians can agree that the source of statistical uncertainty is because you've only observed a finite sample, y1 to n, from some unknown population. So given the entire population here, which I've written informally, is y1 to infinity. You can imagine it as having access to this infinite sampling mechanism. And technically, under some assumptions, the parameter, which is going to be a function of this population, would be known precisely. That is, if you see y1 to infinity, you have no uncertainty on your parameter, regardless of which field of statistics you lie in. What we argue is that when you're being Bayesian and you have this posterior uncertainty, it's fundamentally about the uncertainty in the remainder of the population. So we've seen y1 to n. What do we need to compute this theta infinity? Well, we need yn plus 1 to infinity. And what we're going to do is we're going to argue that the Bayesian targets the uncertainty in this infinite population directly. And this is where the connection between prediction and inference arises. So kind of a taster, this computational scheme is very much akin to a bootstrap. What we can imagine is, given the observations y1 to n, we're going to carry out this kind of predictive bootstrap scheme. And it's going to be equivalent to Bayesian posterior sampling, as I'll show you shortly. So the idea here is we're going to impute this remainder of the population, yn plus 1 to infinity. Seems like a bit of a heavy task at the moment, but I'll go through kind of a practical implementation of this later on. And the important thing to note here is we're going to be drawing from this joint density P of yn plus 1 to infinity. This joint density is going to be assuming correlations because it's going to be a subjective predictive distribution. Now, given this imputation of yn plus 1 to infinity, you're going to compute some parameter theta infinity, and that's going to give you actually a sample from your posterior. So I'll give you a little bit more details about what this looks like in practice in the next slide. But long story short, the Bayesian essentially imputes what they need to know the estimand, and that in this case, in the IID setting, it's going to be yn+1 to infinity. So let's look at a kind of diagrammatical illustration of this. Suppose we had a finite population. This is a little bit easier to envision. So instead of infinity, we have some big capital N. You carry out a study, which is essentially just going to draw a random sample. So here we've drawn a sample of size 2. And suppose our parameter of interest is something that depends on the entire column A, or some function of the columns A, B, and C, such as the average of A, or some nonlinear combination of these two things, averaged over the population. What we're going to do is that now that we've seen two observations, we assume the data is IID, so we can rearrange, and we're going to call y1 to 2 the data points we've seen. I'm going to describe shortly something called predictive resampling, which is this kind of Bayesian Bootstrap-like interpretation. And we're actually going to essentially repeatedly impute y3 to capital N. Each time you impute this table, you get kind of a pseudo population from which you can compute any estimand you want, like any function of A and B, essentially just taking the columns. That's going to give you a parameter estimand. And every time you impute this population, you're going to get a different parameter, and the distribution over these random parameters computed from the population will be precisely your posterior distribution. So more formally, actually, this joint predictive I've kind of left undefined for now. One way to write this Bayesian joint predictive is something called the frequential factorization. Frequential is some work from David in the 80s, which is a combination of predictive and sequential. The idea here, and you can kind of ignore the infinity, just imagine it's a big N for now, is that the joint predictive density on some future population is just going to be the product of the one step ahead predictive. So I'm just going to look at the predictive yn+1 given y1 to n, yn+2 given y1 to n+1, and then you can multiply this, and from the chain rule, this gives you the joint. So let's suppose for now that this is mathematically formal, which it's not. You can impute yn+1 to infinity from this predictive, that is, draw a sample, or you can also define a random variable that has this law. From this imputed population, suppose we had access to some estimate, and there is a little bit of detail here on what this theta needs to be, but let's suppose it's something really easy, like the mean, for example. Because theta is going to be a function of y1 to infinity, and yn+1 to infinity is going to be random, it's going to have a distribution essentially conditioned on y1 to n. So the little y1 to n will be fixed. And there's a really neat theorem from a long, long time ago, which is essentially a Bayesian consistency theorem, but we can borrow those results. And it's based on Dup's consistency theorem, for those who are interested, that shows that under essentially the regular Bayesian parametric modeling, doing this kind of imputation scheme where you draw this infinite population and computing this estimate, where the estimate needs to be quite specific, is exactly the same as drawing a sample from the posterior. So this imputed bootstrap scheme is mathematically and actually almost surely the same as drawing a sample from the posterior. So I mentioned this term predictive resampling earlier, and I've just assumed that you can draw this big joint sample from this joint population. You can actually do it in this one step ahead manner, which is much more computationally feasible. So the idea here is to actually break down this big joint P of yn+1 to infinity, or capital N, into a sequence of one step ahead predictives and draw in this sequential imputation way. So we have this algorithm called predictive resampling, which essentially lets you draw yn+1 to infinity in an online way. So let's say we have the data points y1 to n. We fit a predictive Pn, and we have some truncation parameter capital N, which I'll talk about later, but it's kind of an approximation for infinity. For each of the capital B posterior samples, what we're going to do is we're going to sequentially impute the remainder of the population. So the first step is to draw yn+1 from our predictive. That's quite easy. We just have a predictive. We're going to draw yn+1. The key step here is to get this joint. We're actually going to need to update this predictive. So we're going to essentially treat yn+1, which is simulated, as a real data point. So we're going to now have assumed that we've observed y1 to n+1. We're going to update our predictive distribution. That's going to give us Pn+1. Then we're going to sample yn+2. We're going to do the same thing, treat that as a real observation. And we're going to continue this onwards to infinity. And this is exactly the same thing as drawing from the implicit joint predictive that's a product of all of these one step aheads. The reason why we decide to break it down into this is because one step ahead predictives are really easy to work with. It's quite popular in machine learning to kind of predict the next time point instead of trying to predict this whole collection. But this can be investigated in future work. So given this imputed population, y1 to n, we can just treat this as if we've seen the entire population, we're going to compute some estimate. And theta n is going to be distributed according to our posterior. So I'm going to go through a parametric example now, a very simple conjugate Bayesian model to show you what this looks like in practice. For now, it's been a little bit abstract with these infinite populations, but I'm going to show you that actually in practice, computationally, you can make this direct comparison. So let's start with a traditional Bayesian framework for now. Suppose we have a very easy normal likelihood model where the mean is unknown. We're going to put a conjugate prior with variance 1 on theta. And from conjugacy, we actually know the form of the posterior density. So the posterior is just going to be centered at essentially the sample mean with an extra +1 in the denominator from the prior. The variance is going to be proportional to 1 over n plus 1, again, with this +1 from the prior. But now we're going to actually take a step back. We're going to actually start with, instead, the posterior predictive density, which again is tractable from this model. We know P of yn plus 1 given y1 to n is going to be a normal distribution, again, centered at essentially the sample mean, with a variance equal to the sample variance 1 plus this posterior uncertainty 1 over n plus 1. So let's forget the posterior for now. Let's start with this predictive density directly. It's pretty interpretable. What we're saying is that our new sample is essentially just going to be the sample mean, and our variance is going to be approximately 1, shrinking at rate 1 over n. So predictive resampling is going to be exactly as we promised before. You're going to simulate a data point, and you're going to shove it back into the point. So the first step is to draw yn plus 1 from a normal distribution centered at theta bar n and 1 plus sigma bar n squared. Remember, theta bar n in this case is computed from actual observed data points y1 to n. To update our model then, it's going to be simply updating the sample mean. So we're going to define theta bar n plus 1, our new kind of parameter. It's just going to be the average of your original data points plus this new simulated data point yn plus 1, noting that in the divisor, we've also added a +1. Similarly, the variance is now going to be proportional to 1 over n plus 2 because you've seen an extra data point. And then what predictive resampling means to do is just to continue this onwards to infinity. So we're just going to keep drawing y plus 2, y plus 3, all the way to infinity. We're going to see what happens to this random variable at the end. So a little simulation example here. Suppose we've drawn 10 data points, in this case from the truth being theta equals 2. The point estimate is going to just be 1.84, so that's going to be the place where we start. So on the figure on the left here, we have a plot of trajectories. So along the y-axis, we're going to be plotting the trajectory of the posterior mean, or you can think of it as the sample average of this imputed population. At time 1, this is essentially just going to be 1.84, but you're going to be drawing yn plus 1, yn plus 2, all the way up until yn plus 1000 here. And as we simulate this infinite population, we're going to be computing this kind of running mean. And we can see that for each of these gray lines, it's going to be a single imputed population. We see that as you impute more and more of the population, your parameter estimate theta bar n converges to kind of a fixed point on the right-hand side. I mean, the intuition here is that we've essentially imputed the entire population, so there's no more uncertainty left in our parameter of interest. What's interesting is when you repeat this procedure, so we start again from theta bar n, little n, and you draw a new trajectory, it's going to again converge, but the point that it's going to converge to is going to be different. And every time you impute the population, you're going to get a different value of theta infinity. So let's plot the kernel density estimate of this theta bar at capital N, or you can think of this as kind of the limiting population mean. And we're going to overlay it with the Bayesian posterior density, and you can see that it's pretty much well aligned. And actually, you can prove mathematically that the limiting variable theta bar infinity is exactly the same as the parameter that's distributed according to your Bayesian posterior. So in the predictive framework, this kind of sequential imputation scheme, where you fill in the data that you need to compute any estimate of any parameter of interest, is identical to this posterior sampling. But for now, we've seen that we've actually derived the predictive from the posterior. It seems like a bit of a roundabout way. We started with the posterior, got the predictive, went back. So what we're going to do now is that we're actually going to generalize this. We're going to actually imagine what this looks like when we have a more general sequence of predictives. So that'll be the remainder of the talk. There's a lot of related work that's been really elegant and closely connected to these ideas of prediction. Of course, Dave Finetti's wonderful theorem kind of emphasized that probability statements should only be on observables, and we agree. We think that observables are easy to work with, and these things are verifiable and observable in practice. So yn plus 1, for example, could actually be observed in practice, but the parameter estimate could not. There's also some really great work done in the 80s and the 70s by David and Geiser, which is focusing on the predictive approach of Bayesian inference, essentially treating model evaluation and inference all as a function of predictive and predictors. And what we're doing is essentially taking this one step further. We're arguing that in addition to kind of predicting future data points, it's also important to consider uncertainty in the future populations. More close to the Bayesian nonparametrics literature is these ideas in predictive Bayesian nonparametrics. There's a kind of predictive Dave Finetti's theorem which connects exchangeability in predictive distribution to these posteriors, done by some work by Fortini and Petroni. And there's also going to be this theoretical framework, which I'm going to talk a little bit about, but not too much, on sequences called conditionally identically distributed sequences. The theory was introduced by this wonderful paper in 2004 by Bertie et al. And we're going to lean very heavily on this theory, but luckily there's going to be some really nice intuitions. The idea here is that conditionally identically distributed sequences is going to be a relaxation of exchangeability that has this really nice predictive interpretation. So I'll go through this later on. And there's also been some work that looks at doing similar things about imputing populations, but these have been a little bit more constrained in terms of working backwards or starting with discrete models. And recently there's been some work by Fortini and Petroni, which looks at kind of the connection between these CID or conditionally identically distributed sequences and exchangeable ones. Okay, so now onto the beef of the paper. I'm going to introduce a predictive framework for inference that is based on this kind of predictive imputation idea, but doesn't require the construction of a likelihood, construction of the predictive or likelihood in a prior. We're going to see that there's going to be some notions of coherence. We can't be kind of crazy and just pick any predictive we want. And we're also going to see that there's going to be some connections to kind of robust statistics and how we define our parameter of interest. And then overall, this is going to give us something called the Martingale posterior distribution. Okay, so kind of to summarize what we did before, a very natural generalization is instead of constructing your predictive distribution from a likelihood and a prior, we kind of see that to do posterior sampling, you don't actually need the likelihood of the prior, you just need the predictive. So why don't we start with that as our model elicitation? And indeed, our model now, instead of being a likelihood and a prior, is going to be a sequence of predictives. So we're going to be tasked, and it might seem a little bit difficult at first, but we're going to be tasked with eliciting this one-step ahead predictive. So P of yi given y1 to I minus 1 for data points n+1, n+2, all the way to infinity. And if we take this product, we know this is going to be the joint predictive on the remainder of the population that you haven't seen yet. We're also going to define some parameter, theta infinity, which is going to be some function of this population. I'll formalize what this kind of detail of y1 to infinity looks like. But the key here is that we're not going to be starting with the likelihood and a prior. We're only going to be starting with the predictive. Posterior inference is now going to take two steps. The first step is something that we discussed already, predictive resampling. This is the typical step. Essentially, from this sequence of one step ahead, given y1 to n, you're going to sequentially impute the remainder of the population. And then until we have y1 to infinity, noting again that the first n data points are going to be fixed. So you're going to start at y1 to little n, and then shoot off to infinity. That's one sample. You're going to start at y1 to little n again, shoot off to infinity. That's your second posterior sample. And for each of these imputed populations, we're going to compute a parameter of interest. So now I'm going to formalize what it means to compute theta y1 to infinity, which is kind of vague for now. We're going to be using loss functions, which is quite popular. And the idea here is we're going to be minimizing the expectation of some loss function, where the expectation is going to be taken over this f infinity. So f infinity is actually going to be the limiting empirical distribution. We're going to see shortly that there are some conditions to make sure this exists. But the intuition is quite clear. If we have an imputed infinite population and we take the empirical distribution, this is going to give you essentially a random distribution f infinity. And so taking a functional of this, minimizing this expected loss is going to then give you a parameter of interest. And the final kind of disclaimer is, of course, we can't actually do this for infinity. We only can do this for some large but finite capital N. We'll also see shortly that you don't need this to be very big for you to converge, actually, which is quite neat. Okay, so the question is now, how general is this? Can we just use any sequence of one step ahead predictive densities? And the answer is unfortunately going to be a firm no. There are going to have to be some constraints. And these constraints are going to be weaker than the traditional Bayesian constraints, but they're still going to be kind of intuitive and easy to understand. So the idea here is that because we're working with infinities and we're kind of sampling these infinite populations where we're trying to get uncertainty and tease out some uncertainty for this parameter, we have to take care when we're actually listing this. And so in particular, we need to make sure that these limits exist. So limiting empirical distributions, that is when we impute our population, it doesn't just meander up to infinity, it actually kind of converges to something. And in addition, we need this kind of coherency condition to make sure we're not introducing any bias when we're just trying to get uncertainty. So I'm going to introduce two conditions, which are a little bit theoretical, but on the next slide, I'll talk a little bit about the practical implications. So the first is going to be that there's a limiting predictive distribution, and actually this is going to be equivalent to assuming that there's a limiting empirical distribution. This just means that when you carry out predictive resampling, you actually get a random variable at the end. But a kind of more intuitive way to understand this is if I had access to the entire population, I would actually know what the underlying sampling distribution is. Secondly, we're going to have this unbiasedness condition. So this is going to be saying that for the random distribution P infinity, you can think of this as kind of the posterior distribution over your unknown sampling distribution. We want it to be unbiased. So the expectation, that is the posterior mean of this random distribution, is going to be the same thing as what you start with. And the intuition here is that if you're going to be using predictive resampling to get uncertainty, all of your data is simulated. there's no real information there besides uncertainty. So you wouldn't expect kind of there to be any biases introduced through getting this uncertainty. Fortunately, there's going to be a simple way to satisfy these two conditions, which was the namesake of the paper. So in particular, a Martingale condition is all that is needed for conditions 1 and 2. And so a Martingale, for those who are unfamiliar, is kind of a stochastic process where conditional expectations are going to be equal to the previous time point. So in this case, what we're saying here is that suppose we're doing the first step of our predictive resampling, we're imputing Pn plus 1, and then we're going to update Pn to Pn plus 1. What we require here is that on average, when we update using this simulated data point, we're going to recover the previous predictive. So in other words, by simulating and updating your model, you haven't introduced any new biases. On average, you're just going to end up with what you started with. And I think this is a really nice intuitive kind of predictive coherence assumption. It's saying that our predictive scheme is designed in a way that if we were to simulate from our own model, we wouldn't be introducing any new biases. And I think that's fair because there's no real new information being added. This is actually exactly equivalent to forcing the sequence yn plus 1 to infinity to be this CID condition, so this weakening of exchangeability, which is introduced in this Bertie et al. Paper, but I won't have time to talk about too much of that today. And the key here is that this is actually kind of a predictive invariance assumption. So we're assuming that as we simulate our populations, we're not introducing any bias, and in a sense, it's a weakening of exchangeability because you just need this coherence to hold for the next data point. But again, these are technical conditions to ensure that the predictive exists, and we're going to talk a little bit about how to construct the predictive that satisfy these conditions. The parameter of interest is much more familiar. It's easier to work with. The way to think of this is that what is the parameter that you actually want to know given access to the sampling distribution? So for those who are working in robust statistics, this should be pretty familiar. You're looking at the argument of some expected loss function. And so the median would give you, the absolute value would give you the median, whereas the squared value would give you the mean. Similarly, you can be interested in some parameter indexing a model, but you're not sure that that model is correct, then you would choose the negative log likelihood as the loss function. But it's a pretty general framework, so we didn't spend too much time talking about this. So to summarize, essentially, the Martingale posterior distribution is to specify a sequence of predictives that satisfy this somewhat constraining predictive coherence condition. But given that we've managed to construct this predictive model, we're going to impute yn plus 1 to infinity through this sequential imputation scheme. Given this imputed population, we're going to compute our parameter of interest. And this random theta infinity is going to have a random distribution, which we're going to be calling our Martingale posterior. Now, we've already seen that there's a special case. If our predictive distribution is the one step ahead implied by the likelihood of the prior, then this is going to give us the exact same thing as the Bayesian posterior. I'm now going to talk about two generalizations, which might be more new to those who are not familiar with Bayesian nonparametrics. If you pick your predictive sequence to be the empirical distribution, which is quite intuitive, we're going to return something called the Bayesian Bootstrap, which has some really nice properties, and we're going to show has some really nice interpretations as well. But the methodological contribution here is that actually we don't even need things to be exchangeable. If we weakened it so that it's just CID, this predictive coherence condition, then you actually have a much broader class of Bayesian models. And I put in quotation marks Bayesian because if it's not exchangeable, then technically there's no likelihood of prior representation. But under this predictive framework, we show that you still have kind of all the core ingredients you need to carry out posterior sampling. And so for this, we're going to be using something called the Bivariate copula, which I'll talk about shortly. But this is kind of closely connected to these online updating predictors. Let's start with the empirical distribution. So I'm going to talk a little bit about something called the Bayesian Bootstrap, which arises really naturally from this interpretation. The Bayesian Bootstrap is really, really old, actually, but there's been many kind of ways to reanalyze it. And we're going to use the Bayesian Bootstrap as our workhorse to compare Bayesian and Frequentist uncertainty in a way that we think is quite intuitive. So the empirical predictive is super straightforward. It's kind of the archetypical non-parametric predictive. The idea here is that if we've seen data points y1 to capital N, we're going to expect our new data point yn plus 1 to be essentially the empirical distribution of the data we've seen. We're going to give each of the data points mass 1 over capital N, and that's our predictive, full stop. And we're going to be defining this for the entire sequence, but again, it doesn't really matter because every time you see a new data point, you're just going to essentially treat it as a real data point and then look at the empirical distribution over those. What's interesting is that if you carry out predictive resampling, so the idea here is to draw yn plus 1 from the empirical distribution, plug it back into the empirical, draw a new one. It's clear that yn plus 1 to infinity will only ever contain repeats of the data you've already seen, right? Because you started off with this discrete support, you can only draw data points from y1 to n. And so what that means is that the limiting empirical distribution, or kind of the evolution of this population, is going to just be a reweighted version of the empirical distribution. So indeed, if you carry out predictive resampling with the empirical, it's going to be exactly the same thing as reweighting your data points from this flat Dirichlet distribution. So this Dirichlet distribution is going to be essentially a sequence of weights of size capital N. It's going to add up to 1, and it's essentially going to be uniform over this simplex of n-dimensional numbers. But the idea, I'm going to show you a little animation about what this looks like later on. So the Bayesian Bootstrap, it's going to be essentially a special case of the Martingale Posterior, as introduced in 1981 by Rubin. The idea here is that instead of predictive resampling, we know what the limiting empirical distribution is. There's no need to actually simulate it. We know that it's going to be this Dirichlet reweighted distribution, so we're going to compute that. Again, we're going to write F infinity for our limiting empirical because we know that it's just going to be reweighted version of the empirical distribution. And then you're going to compute this argument of the expected, which again simplifies because F infinity is only going to have a discrete support. So you're going to be minimizing this weighted sum of this loss function where W is going to be random at each posterior sample. Now the Bayesian Bootstrap actually has a lot of really nice properties on a model misspecification. You can kind of prove things that show that the posterior on this parameter under some assumptions is really robust. It's also equivalent to the Dirichlet process, which you might be familiar with when you derive kind of the prior to zero. So it's kind of a non-informative version of the Dirichlet process. Some work that we've done is to show that it's actually computationally really fast and parallelizable, handles multimodality in quite a special way compared to traditional MCMC methods. But I'm going to talk a little bit more about this later, is that F infinity is guaranteed to only have support on the data points you've seen. There's going to be some scenarios which this is going to be problematic. So in particular, if theta requires smoothness, then the Bayesian Bootstrap just fully breaks down. And I'll give an example of that later on. But just for kind of those who are not familiar with the Bayesian Bootstrap, I made this little animation during my PhD, and I spent a lot of hours on this stuff and trying to milk it out through all of my talks. The idea here is really simple. Our parameter is going to be the slope and the intercept that minimizes kind of the least squares. So we're not going to assume that the model is actually linear, but we're just interested in this parameter that minimizes the square difference. Suppose we've seen these blue data points, these XY pairs, and we can plot the maximum likelihood estimate in gray. The Bayesian Bootstrap is really simple. You literally just draw these Dirichlet weights on the bottom left. Each time you draw them, it's just going to be randomly reweighting the data points, but it's going to make sure the weight sums up to 1. And by reweighting these data points, you can then fit kind of a weighted least squares, because that's just going to be the function of this randomly reweighted distribution. That's going to give you this random red line, this random intercept and slope. And if you plot the distribution of this beta and gamma, this intercept and slope, you're going to get essentially a bivariate posterior distribution. So this is kind of, in a nutshell, what the Bayesian Bootstrap looks like. And it generalizes to much more complicated loss functions. I'm now going to talk a little bit about kind of the interpretational aspects of this Bayesian Bootstrap and why I think it's going to be a really nice workhorse to compare between the Bayesian and the Frequentist. So on the left here, we have the Bayesian Bootstrap. For each posterior sample, we're going to do predictive resampling, at least conceptually. We don't actually need to do this in practice. You're going to be drawing yn plus 1 to infinity from this empirical distribution, where sequentially you're going to draw from the empirical, then you're going to treat that new data point and update, basically a Polyar urn. You're going to compute the limiting empirical distribution from this entire population and compute the estimand theta from F infinity. Now, Efron's bootstrap is the Frequentist bootstrap, which you're going to be using to compute things like standard errors, but there's a nice analogy here, where instead of sampling yn plus 1 to infinity, you're going to be resampling y1 to n. So you're going to loop over y1 to n. You're going to sample yi star from this empirical distribution. You're not going to update fn because you're actually treating fn as an approximation to f0. And then fn star is going to give you some random empirical distribution, and you're going to compute some estimate. So there is kind of this nice overlap between the Bayesian and the Frequentist bootstrap. And kind of in summary then, the way we like to interpret this is that they're both bootstrap schemes, but the key difference is that the Bayesian imputes a different side of the data. So you've observed y1 to n. The Bayesian is interested in what they need to know our estimand. So we're going to impute yn plus 1 to infinity, and we're going to compute the estimand theta 0. Whereas the Frequentist is going to look backwards in time. It's going to consider what other y1 to n I could have seen and look at the distributional properties of the estimator theta hat, which is going to be computed from y1 to n. I like this comparison because both methods start with essentially the same thing. We start with the empirical distribution. We do some version of resampling. One resamples with replacement, the other resamples in this Polyar urn scheme. But the key thing we want to highlight here is that we fundamentally differentiated between Bayes and Frequentism without the need for some prior distribution or likelihood in the first place. Nowhere here have we kind of explicitly discussed what the prior distribution is over any parameter or distribution. We just started with the predictive. And I think this is kind of a nice way to compare Bayes and Frequentist on equal footing. Essentially, you're looking at different sides of the population. Okay, so as promised, I'm now going to talk a little bit more about some new methodology. I'm only going to go through a simple example, but in the paper you can see some more general examples. What we're going to do is we're going to work with these bivariate copula updates, and we're going to be able to tackle some tasks that the traditional Bayesian Bootstrap can't. So as I discussed before, the Bayesian Bootstrap is super intuitive, but it only returns discrete F infinity. So this means that, for example, if your parameter of interest is something like a density, or the number of nodes in F infinity, the density of that, or in a separate setting, if you were interested in, for example, a parameter that's a functional of this regression function, such as the mean of y given x, the Bayesian Bootstrap can't handle that because it assumes everything is atomic. So what we want is to have kind of a more general recipe, essentially generalizing the Bayesian Bootstrap that has this nice interpretation, satisfies the Martingale property, primarily because we need this for predictive resampling. But the key thing here is that it has a continuous density, and it's also not parametric. We're going to see that actually you can define these updates in a recursive manner, kind of like the empirical distribution, and utilizing this recursion for actual computational feasibility. And I like to think of these methods I'm going to discuss shortly as essentially generalizations of Bayesian Bootstrap, smooth and Bayesian Bootstraps, you could say. What we're going to rely on is something called the bivariate copula. So let's define this predictive PIY. This is going to be the predictive density at some test point, presumably y plus 1, condition on y1 to little I. And what we're going to do is we're going to have this recursive update where the update is only going to take the new data point yi plus 1, combine it with the predictive, and compute p of I plus 1. So the idea here is you don't need to refit your model to the entire data set y1 to I plus 1. You just need the old predictive, your new data point. You can compute this kind of recursive update. And the recursive update is going to take the form exactly here. So it looks a little scary at first, but essentially what we're going to say is our new predictive is going to be a product of our old predictive and some term here. And I'm going to break this down shortly. This term is going to be a bivariate copula. So for those who are unfamiliar, a bivariate copula, CUV, is just a bivariate density. It takes as input uniform random variables. So U and V are going to lie in between 0 and 1, and they're going to have uniform distributions marginally. And so the bivariate copula is essentially going to be modeling the correlation between these two uniform random variables, U and V. And there's a lot of literature to show that copulas essentially model the dependence between U and V, independent of the marginals. So you don't actually need to care about what the marginal distributions are. You just want to know how U and V are correlated. So let's go back to the equation here. C, and ignore the subscript for now, is going to take two inputs, U and V. The input on the left-hand side is going to be the CDF at this test point y, and the input on the right-hand side is going to be the CDF of this test point yi plus 1. That's the data point we're going to be updating. So we can see that throughout the update, yi plus 1 only comes in through this second term in the bivariate copula. One way to think about this is actually measuring some kind of distance. You could think of the copula as capturing kind of how far is my due data point for my test data point, and I'm going to kind of allocate density accordingly. The other way to think about this is that the bivariate copula models dependence. This test point y is going to be test points for yi plus 2. So what the copula is actually modeling is this predictive dependence between sequential data points. So suppose I have yi like a predictive pi, I see a new data point yi plus 1. The copula models my predictive dependency. How much am I going to update my predictive based on this new data point through this idea of the correlation? Now it's a little bit abstract here. So on the next slide, I'm going to show you a concrete example, which is going to look very much like a kernel density estimate, which is quite nice and easy to interpret. But before we do that, we're actually going to talk a little bit more about why these bivariate copula updates are quite interesting. So the bivariate copula is actually really general. You can prove that every single Bayesian model has a sequence of copulas. So in particular here, the new predictive density is going to be some function of the likelihood in the posterior. And you can prove that this is actually going to correspond exactly to a bivariate copula. Now pointing out the subscript I plus 1, it's a sequence because at each time point, the copula doesn't necessarily have to take the same form. I'm going to give an example on the next slide of what this looks like. But in general, you know that if your prior is kind of what you choose and the likelihood is some fixed form, these integrals are probably not going to be tractable. And that's exactly the problem with doing Bayesian inference this way. You can't actually compute these copula, so it's not very useful. The idea which was introduced from an older paper is that actually we can pick this copula sequence directly in a tractable format. It doesn't necessarily have to correspond to a Bayesian model anymore, but we can show that it actually retains the Martingale condition. So any construction, any sequence of predictives constructed of this form, indeed will retain the Martingale condition. And indeed what we're going to do is we're going to turn to Bayesian nonparametrics to come up with an update. So this is kind of a very long and arduous roundabout way, but fortunately the update, the predictive update is going to be quite intuitive and easy to understand. We're going to be relying on this Dirichlet process mixture model, which we already know has connections to the kernel density estimate. But now we're going to see a much more explicit kernel density estimate type update. Okay, so the update is given here. I'm going to break it down term by term. And essentially what we argue here is that this update is basically a nonparametric kernel density estimate. So let's look at the equation. There's going to be two sides. On the left-hand side, we have our new predictive density as some test point of y. On the right-hand side, we actually have a weighted sum of two terms. So the first term on the left is 1 minus alpha I plus 1 p of I. So this is going to be essentially a weighted sum of the old predictive density and some new term here. On the left-hand side is just pi. On the right-hand side, you have this product of this copula and the predictive density, which is not very easy to interpret on its own, but we're going to plot it, and we're going to see that it essentially looks like a kernel centered at our new data point, yi plus 1. So just some notational detail here. C is going to be a Gaussian copula density. It's just kind of something you can pull off the shelf. This alpha I is going to be a term that shrinks with 1 over n. The idea here is you're updating your data points with weight 1 over n. And finally, rho, the subscript in the copula, is going to be a term between 0 and 1, and it's exactly the same thing as a kernel density estimate family. Okay, so we're going to look at this equation, and we're going to break down each of the terms in this figure. So on the bottom left figure, we have our new data point in this black dot. So we're going to be trying to update our predictive using this new data point, y equals to 2. Our old predictive is going to be shown in this dotted line. So it's simply a bell-shaped curve centered at 0. That's what our predictive is. But now we've seen this new data point, y equals 2. How are we going to update our predictive? So in this plot, in the solid line, I plotted what this right-hand side sum looks like. This is the product of the copula and the predictive. And you can see that for different values of the bandwidth, it essentially just looks like a kernel, like a Gaussian kernel, like from the kernel density estimate, centered at the data point y equals 2. Now, as you increase the bandwidth closer and closer to 1, that's getting darker. We can see that the kernel gets more and more peaked about the data point. So again, it has this kind of smoothness type interpretation. The one thing that I think is quite interesting is as we decrease rho closer to 0, not only does the kernel get wider and wider, it actually kind of shifts towards the left. It's no longer centered about the data point y equals 2. And actually what's formally happening here is that kernel is going to be regularized towards the previous predicted distribution. So essentially what this gray solid line is going to be is kind of an interpolation between the gray dotted line and a peak at y equals 2. So now if we want to implement the equation above, we're going to be taking a weighted sum of this gray dot and this respective solid line. So we see that on the right-hand side. In solid, we have the new predicted density that's updated with y equals 2. Again, we see that it's essentially just the old density with a big bump at y equals 2, where the peakness of the bump is dependent on this bandwidth. So what we see here is that actually what we're doing with these copula updates, inspired by the derivative process, is essentially an online kernel density estimate, where you're going to take a weighted sum of your old density and you get add on a kernel at your data point. But one thing that I have to emphasize here is that it's not just a Gaussian kernel. The reason why we need to go through this machinery is that if you just use the kernel density estimate, it's not going to be a Martingale. You can actually prove that it'll never be a Martingale. Whereas here, we're actually having a data adaptive kernel. So essentially, instead of adding a normal center at y equals 2, we're going to have this data adaptive kernel that's a little bit regularized towards our previous predictive density, which is going to give us the coherence property. But kind of diagrammatically, it's just a glorified kernel density estimate in an online fashion. Okay, so one thing that's really interesting, which I don't have too much time to go through today, is that because it's recursive, if I want to carry out this predictive resampling approach, which might look a little bit expensive, it actually ends up being really, really cheap. What you actually have, okay, really cheap is misnomer, but it's going to be kind of simple at least. The idea here is that when you update this predictive density, you can see in equation 2 here, the new data point actually, sorry, in the previous slide, the data point only ever comes in through the second input in the copula. We're never going to see yi plus 1 isolated. It's always going to be the CDF p of I of yi plus 1, where yi plus 1 is going to be actually drawn from the distribution pi. And we know that if you draw a random variable and compute the CDF of this random variable, it's going to be simply a uniform distributed variable. So instead of actually having to simulate yi plus 1 to infinity, all we need to do is simulate a bunch of uniform random variables and plug them into our update. And that's indeed how you carry out posterior sampling in this case. You just draw a big number of uniform random variables, you compute this online kernel density estimate, shoving this uniform random variable into the second input, and voila, you have a posterior sample. Some more practical details with these methods is that there's going to be some connections to Bayesian model selection. To pick this bandwidth very naturally is to use this log frequential log likelihood. Essentially, this is just the marginal likelihood. And you can use this to tune basically how much you want to update and also how smooth your density is. We also actually provide extensions to the multivariate and the regression setting. So here I've only showed you the one-dimensional density estimation, but the regression setting is perhaps more interesting, where you can have smoothness as a function of x. And there's also, using these updates, you can actually prove some pretty useful theoretical properties, such as consistency and kind of the rate of convergence to the posterior. Okay, so to end the talk, I'm going to go through a pretty classic example. We're going to look at a density estimation example using this very widely used galaxy example. It's a little bit old-fashioned. Suppose we've seen 82 data points, so these are just going to be samples from an unknown density. What you can do is you can actually, the traditional way to analyze these methods is to use a Bayesian nonparametric model, such as the Dirichlet process mixture. It's essentially a pretty complicated nonparametric model, and then you can get posterior samples of the actual entire density. So your parameter now is going to be a curve, it's going to be the density. And you can compute the point estimate of this density as well as credible intervals. So on the figure on the left here, we actually have the posterior mean as well as the posterior 95% credible intervals using the Copula method. So we're going to be fitting our predictive to our data points. It's going to give us some bandwidth, in this case 0.93. Then we're going to predictive resample, and then we're going to see the distribution of those random densities. And we're going to plot that in this posterior mean and credible intervals. On the right-hand side, we have the traditional Bayesian nonparametric method that goes through MCMC, and you compute posterior density. We can see that the posterior means are pretty close in value, not exactly, but quite close. And the uncertainty is also relatively similar. You have uncertainty around the peaks, but you can argue that maybe there's a bit more uncertainty in the Copula methods. But the key here is that on the left-hand side, there's nowhere that we've used any kind of Markov chain Monte Carlo. In fact, there isn't even a likelihood or a prior. All we have is a density estimator and this predictive resampling scheme. And we've managed to get essentially Bayesian uncertainty in the exact same way. One final comment is that the computational kind of details for the Copula method are really different. So it's not exactly easy to compare one-to-one. But for example, if you had access to a few CPUs and access to a GPU, then the Copula methods are particularly parallelizable. Essentially, it's just a lot of grid multiplications. It's actually just a very big matrix multiplication. And so in this case, it actually takes only 2.5 seconds to both estimate the density, compute the bandwidth, as well as carry out 2,000 posterior samples. Whereas MCMC using 4 cores, I think, took about half a minute. So it's not generalizable, these computational properties, but it's definitely different. And so if you have access to parallel compute, for example, it can really speed things up. And this is kind of in vein with the Bayesian Bootstrap type methodology. Aside from actually computing kind of uncertainty on the density, you can also go back to some parameter that you're interested in. So what you can say is that you're interested in some functional of the density, so theta of little f infinity. In this case, suppose we're interested in the modes or the quantiles. Again, these things are going to be slightly harder to compute with the Bayesian Bootstrap because that returns a discrete empirical distribution. You can see here that the posteriors are different between the Copula method and the Dirichlet process, but they give similar type of answers. So the Copula says, we think there's going to be around 4 modes and some right skew tail, whereas the Dirichlet process mixture model thinks there's going to be 5 modes. But you can essentially carry out regular Bayesian parametric inference as well, but it's not as cheap. Okay, so now that I've introduced the work and gone through some of the body, I'm going to discuss some of the conclusions. So from this paper, we've kind of introduced this new type of thinking, this foundational type of thinking, where we argue that Bayesian inference is fundamentally about imputing y=1 to infinity. Even if you want to use your likelihood prior, we argue that what you're actually doing is considering what different y=1 to infinity populations can be, and reasoning about the uncertainty on those. We find the Bootstrap interpretation to be really insightful. Bayesian uncertainty arises simply from the side of the population that you're interested in computing uncertainty for. It doesn't necessarily have anything to do with a prior, but you're free to use a prior to construct your predictive. It's also kind of a broadening of the methodology, at least we hope so, in that you can generalize Bayes beyond the likelihood of prior. Again, the Bayesian parametric or even the non-parametric framework is a special case of the Martingale posterior, but you're now free to choose at least a broader class of predictive distribution and parameters of interest. Unfortunately, these are still constrained. You need this Martingale condition. It's not that easy to apply in practice. And so I'm still pretty curious to see how far this can go. Can we actually, for example, use any general machine learning model as a predictive? I don't know the answer to that. But we have seen that bivariate copulas are a particularly useful tool. A, because they're quite intuitive, and B, also because they have this guaranteed predictive coherence condition. You can actually use these Copula methods to essentially do density estimation and regression, again, without a likelihood in the prior, and get uncertainty on your functions or your parameters of interest. So thank you so much for your time. This paper is still on archive. We're waiting for JRSSB to put it out with the discussion, but I'm really happy to take any questions now.